Starting?
It's called Dungeons.
Okay.
Yeah, that's totally correct. And then if you enter this, it'll hit
Awesome. All right, I think we'll get started. Welcome everyone. Welcome to the newest and latest Smart Mobility Connection seminar. My name is Sarah Cho, and I am a Traffic 21's Women in Intelligent Transportation Fellow. So this is really an opportunity to hear from our researchers and kind of see what everyone's up to, facilitate discussions and collaboration amongst the community here at CMU. And so today we'll be hearing from Professor Ham Ho. And she is an associate professor in the Civil and Environmental Engineering Department with a courtesy appointment in the Electrical and Computer Engineering Department. Her research really introduced a new concept of structure as sensors, as you will be hearing from today. And essentially it uses physical structures like buildings or vehicle frames to be user and environment aware. So she received her PhD in Civil and Environmental Engineering, and also a master's degree in Civil and Environmental and Electrical Engineering from Stanford. And she received her bachelor's in Mechanical and Aerospace Engineering. So without further ado, I would like to introduce Professor Ham Ho. Please join me in welcoming.
Hey everyone, nice to see you all here. My name is Young No from Civil Environmental Engineering. Today I will talk about, I'll introduce the concept of structures as sensors, which uses the structures, particularly today I'll talk about vehicle structures, to indirectly monitor humans and the surroundings. So our daily life these days heavily depends on civil structures like buildings, water system, bridges, and transportation systems. And we're continuously interacting with them, physically interacting with them. So by making these structures smarter, we can take various advantages. For example, by making these structures aware of their health status or damage status, we can prevent catastrophic events such as bridge collapses, train derailment, and also achieve more efficient operation of this system and provide more convenient or user-centric applications like providing personalized services, more secure systems, and even improve their healthcare. So to achieve all these nice goals, we need to have smart sensing systems. But having a sensing system for this civil infrastructure is very challenging because of several reasons shown here. So first of all, many of these infrastructures are very large scale and complex. If you think about the road network and rail system, there are thousands of miles of these networks out there. So this makes the sensing system very expensive. There's also a lifetime mismatch problem. So do you guys know what's the expected lifetime of buildings or roads or bridges when the designers design? 50 years, 100 years? Sometimes you see these structures 1,000 years old, like some parts of Asia and Europe. So that's the scale. What about the sensors? Do you have any idea of the lifespan of sensors? 3 years?
we go 100.
That's good. That's very optimistic. Easy example will be, think about how often you change your phone. Your cell phone has a lot of sensors in it. About 2 years, 2 to 5 years. So that's about the lifespan. So this huge mismatch in the lifetime between the sensing system and the structures that we're monitoring requires us to have multiple updating throughout the lifetime of the structures. So this will make the overall system more expensive. And there's lack of dedicated sensors. Is there a sensor that tells you directly what is the current damage state of this bridge? No. Or is there a sensor that tells you how happy people are in this building space? Or how productive they are? No. So this lack of dedicated sensor problem requires us to collect either a lot of different kinds of information and merge them together, or have experts look at it, analyze, and try to make sense out of those data. So this will make our sensing system seriously more expensive. So regarding these sensing challenges, my first research interest is in how we can enable existing structures to sense in a more maintainable way. And to address this research question, I've been taking the indirect sensing approach, where we try to infer the desired information from the responses of something else that's much easier to measure sense, instead of trying to directly measure the sensing target. And specifically, I've been using structures as sensors, where we measure the ambient structural responses that are affected by the structure itself, the environment surrounding the structure, as well as the human users within the structure. So this way, we're making the sensing hardware much simpler, because one type of information contains multiple different types of information in there. And this indirect way of sensing the signal provides more non-intrusive and passive way of collecting the data. So it has many advantages, but nothing is free. There's no free lunch. So indirect sensing has its own challenge. First of all, these structural responses tend to contain a lot of noise. So in order to understand this noise and clean them up, we need to have a lot of data. And as I mentioned, these structural responses is a complex mixture of different types of information. So again, to understand these different components and being able to decompose this signal into different parts and extract only the desired information out of it, we need to have even more data. And then all these noise level and the complexity of the mixture all changes over time, meaning we need seriously even more amount of data. So I also tell people that my research is to work with garbage signal, very noisy, seemingly useless, and trying to recycle it so we extract something useful out of this garbage data. So let's look at this data problem, because it seems like you need to have a lot of data to salvage information out of it. But getting the real data is very difficult in real life. So for comparison, let's look at the cyber world. There are close to 300,000 tweets per minute published on Twitter. Google receives over 4 million search queries a minute. Facebook gets over 2 million contents per minute shared by the users. So you see that getting a lot of data in the cyber world is relatively not too difficult. Whereas let's look at the physical world. Can you imagine damaging a bridge 100 different times in all different temperature and traffic conditions? How about asking a person to walk a mile 1,000 different times in different speed, different shoes, different excitement level? What if that person's like your grandma? You don't want to do that. So this high-dimensional problem with the data scarcity, especially the labeled data, is a fundamental challenge whenever we're using machine learning or data analytics in the real-world problem. So in addition to my first research question about sensing in a maintainable way, I've been working on this problem of how can we enable the existing structures to understand with minimal training requirements. So to address this question, we've been working on developing many of physics-guided data-driven approaches. Let's look at it more closely. Under the structures as sensor framework, we have sensing targets like the surrounding environment, users, human users, and the structure itself. And all these, the states of the sensing target will affect the response of the structure, which we indirectly collect the data through these structural responses. And the collected structural responses will be sent to the learning module, where we first extract the features by cleaning up the noise, align the signal, and characterize them. And then the extracted feature will be sent to both data-driven and physics-based models. And these different models will interactively extract the desired information from. And then the extracted information will be sent to the decision-making module to improve the performance of the sensing target, as well as the performance of the sensing system itself. So in this I'll be talking mostly about the learning module. And this learning module has two different parts that I've been focusing on. The first part is about feature extraction by using physics-based models, and also then a physics-guided learning module, second part. But due to the time limit, I heard I only have 30 minutes today. I'll be focusing mostly on the feature extraction part. And given so we've been using various structures like building structures, vehicle frames, human body structure, but I'll be focusing on the vehicle structures. So let's talk about our vehicles as sensors project, where we use the train responses to monitor the tracks and bridges. And this is a collaborative project with Professor Jacobo Biela and Jim Garrett, Mario Burgess in civil engineering, as well as Joanna Kovacevic, who was the former ECE faculty at CSE. And it's also supported by the University Transportation Center here at. So for this project, we're all familiar with the national challenge of deteriorating infrastructure, and in particular, maintaining the rail tracks for the trains is a very challenging task because of this large scale of the rail network. And the current practice for detecting damage or maintaining these rail track is heavily depending on the human reports. The human drivers will be driving the train across different areas. And if they find something's wrong, they're going to call in the transportation center and ask them to go and check what's wrong. So it's very labor intensive, costly, subjective. A lot of damage can be just sitting there until it gets detected. So of course, the research community has been working on this problem and has developed a lot of direct monitoring and non-destructive evaluation methods using cameras, infrared, so the ultrasound or laser of these high-tech sensors. But again, due to this, the large scale of the structure, it's very expensive to both instrument and maintain this sensing system. So to address some of these challenges, my group has been working on developing Thomas the Tank Engine. So these regular trains, operational trains, travel across the whole nation every day, and for some parts multiple times a day. So why don't we make these trains smarter so we can use them as sensors and they can go and identify, quantify, localize, or categorize different kind of damage happening on the vehicle itself, as well as on the rail tracks, roadways, and the bridges. And they're using only the onboard sensing system in the operational vehicle. The basic idea is there's a train instrumented with their sensors to collect their train responses. It will be continuously collecting the data as it travels across the nation. And the signal is sent to the classification system. And whenever we detect some abnormal behavior coming from the tracks, or the interaction between the vehicle and the tracks, the information will be sent to the transportation authority, and they can send out the people to further inspect the problematic areas. So using our vehicles as sensors approach, we can take various advantages, such as it involves much lower installation and maintenance costs because there's no installation needed on the infrastructure itself. Everything goes into the car, the vehicle. So by instrumenting just one train, we can monitor multiple segments of rail tracks and multiple bridges. So it's a very efficient way of collecting the information about the infrastructure. And there's no need to stop the traffic, which is also the cause of lots of cost in inspecting. So using this system, we can notify the drivers any risky situations that's upcoming in near real time. And we can achieve the condition-based maintenance, scheduling, and then resource allocation rather than time-based methods. We can also enhance the overall transportation reliability. So it has a lot of advantages in its approach. But again, there's never free lunch. So just like any other interesting project, this one also has several research challenges. One thing is the train vibration response depends on many different things, including the operational condition of the train, such as the train speed. So if there are two blocks, depending on how fast you drive, you're going to see different signatures in the train response. And also it depends on the train properties, like the mass, the stiffness. So the mass of the train will change in rush hour versus non-rush hour. The stiffness will also change as the suspension system wear out over time. So all these dependencies may mask the changes happening in the train vibration responses due to the damage in the track or the changes in the track. So it's very difficult to just extract out only the track information out of the train responses. And even if we can extract any changes happening due to the track, the physical interpretation of the track changes is very difficult, especially if we're using pure data-driven approaches. So here you can see that the key idea we need to find out is how to find effective features that we can make physical interpretation with. So to do that, we started with modeling the train responses. So under the assumption that the vehicles are linear and time invariant system, we can model the track profile for the roughness as our input to the vehicle system, which has the parameter h. And then we can compute the vehicle response as the convolution of these two parameters, the input track profile and the vehicle system. So theoretically, if the properties of the vehicles are all known, then the track roughness, we can find it from the vehicle responses. It's an inverse problem by solving this optimization problem. So there's formula and solution available out there that we can apply. But then the issue is, these vehicle properties in real life is unknown to us. And it may change over time, as I mentioned before. The mass will change, the stiffness will change. So this optimization problem becomes unstable, or it's an ill-posed inverse problem. So that means we need to better define the problem as a well-posed problem using further constraints. So to come up with more constraints in this optimization problem, we made several observations from the data we collected. So the first observation is that the train's suspension is mostly activated by a few major bumps that exist in the track naturally, like joints and switchgear, as well as the defects. So this means we can make sparsity approximation about the track roughness profile. The signal can be assumed to be stable. Another thing is the train's fundamental mode of vibration tend to dominate the overall response. Meaning we can take the single degree of freedom approximation about the train demand. And then by realizing that we only need an approximate track profile rather than having a very accurate like 3D reconstruction of the track profile, because our goal is to just align the signal, extract the feature, and do the damage detection. Our goal is not to reconstruct a very accurate model of the track. So this justifies the fact that we can make various approximation about our problem. And by doing that, here's the new problem formulation. I won't go into the details of the math, but it basically shows that, like, subject to, there are two constraints. The first constraint is the sparsity in the roughness profile. And then the second one is the single degree of freedom approximation. So to solve this optimization, now there exists a solution to it. It's well posed, but then the computational load is high on solving this optimization. So to make it solvable in reasonable timing, we developed iterative track profile feature extraction method. And to show you how this method works, let me start with the actual train response. So here, x-axis is the position of the train, ordered from the GPS on the train. Y-axis is the acceleration, so it's representing the vertical vibration of the train as it's traveling across the track. This shows very short, 1 meter of 1 meter, I think, 1 kilometer of a track. And then the first step is to initialize the roughness, the track roughness R. The orange curve here shows the just randomize some initial value of roughness R. And then given this roughness, find the best impulse response function of the vehicle H. So at the bottom figure, I'm showing the updated sparse approximation of the vehicle response by convolving the initial roughness R, the initial guess of the roughness, and the vehicle response function or impulse response function we found. So you see that the orange curve and the blue curve are not matching very well because it's only the first iteration, and we made a random guess about the roughness. It's not going to work well. And then the third step in the iteration is given this vehicle response function H, we update the bump location for the track roughness R. Okay? And here's the new result. And if we blow up some part of it, you can see that even in the first iteration, by completing the third step, you see the orange curve is now matching the blue curve a lot better. And then a lot of the noise and the harmonic components are gone. So now you repeat this step 2 and step 3 until the solution converges. And we found out that in each iteration, the solution either improves or the performance stays the same. So the convergence is guaranteed. And in our problem, usually 6 to 8 iteration was enough to have the solution converge. So it was computationally very efficient. So to prove or validate how well this feature extraction method works and how effective it is, we've been collaborating with the Port Authority of Allegheny County to instrument our system into the Pittsburgh light rail system, also called the T. And here this picture shows one of the trains that are instrumented. There are 2 trains that are currently instrumented. So in 2013, we first met with Port Authority and figured out where would be the nice place to put our sensors and the data. And we finished the instrumentation by September 13. And since then, it's been continuously collecting the data and monitoring the rail system over 5 years. So every day, each train comes back with 10 gigabytes of data. To show you the scale of this deployment, this plot here shows the GPS track of the train laid over the Google Maps. It's a 9 by 20 kilometer map. And you see at the top here, on the top in the north is the Pittsburgh area. You see the 3 rivers meeting. And in the downtown, we lose the GPS signal because the T goes underground. That's why there's a straight line, yellow line. So from these data, we applied our method, and I'll show you some of the results here. So the plot on the left-hand side is the raw signal we collected from 145 different passes across the same segment of the track, 50-meter segment of the track. And as you can see that it's very noisy, garbage signal. So it's very difficult to compare the signals coming from different passes. So on the other hand, the plot on the right-hand side shows the result of our algorithm. So it shows the sparse approximation of this signal. And you see that most of the noise is gone. Signals look a lot like each other, so they're comparable now. And we can also align the signal. Signal alignment is necessary because this T is human-driven, meaning it's gonna be driven at different speed, different parts of this track. And also there's a GPS error. So the x-axis actually contains a lot of error too. So we do need to do a post-processing of signal alignment. So now it's much cleaner. We decide to use this as the feature to detect the changes happening in the track. So now let's see how effective this feature is. So for this second level of evaluation, we used the case study of camping because Port Authority wouldn't allow us to go out and damage the track. So what we did is they do a maintenance called a tamping, which means they bring in these vehicles to lift up the rail. to correct their geometry and also put the gravel back, because these gravels or ballast, as the train uses the track for a long time, they all get scattered, and it changes the stiffness of the substructure. So we will compare the signal collected before and after this maintenance has happened. So here's the result. X-axis again shows the position of the train, collected from the GPS in the train. Y-axis shows different passes. So I'm showing a 3-kilometer segment of the track, 100 different passes, 100 different days. And the white dotted line here shows the changes happening in the track. There are 3 different segments of the track that are tamped on 3 different days. So let's take a closer look at one segment of the track here. So among these 4 figures, the top figure shows the raw signal collected from the train. That's the vertical vibration of the train as they travel across this 250-meter segment. Second one shows the bump location, or the track roughness R that's extracted using our algorithm. Third figure here shows the sparse reconstruction of the train response, meaning the convolution of the bump, or the track roughness R, and the vehicle response function H. Okay? And then the bottom figure just shows the first and the third figure together to show how well they match. So the third figure is just picking out the major responses of the train happening in the first signal. So then we decide to use the height of the first bump as the feature. Here's the figure showing x-axis is the pass number, y-axis is the height of the first bump. And you can see that there's a huge change happening between pass number 54 and pass number 55. And that's actually where the tamping actually occurred on this segment of the track. So by roughly defining a threshold around 0, we can detect when the tamping has happened and where the tamping has happened. So using our method, we're able to reduce the feature dimension by more than 100,000 times. And we can also make a physical interpretation and use the amplitude of the feature and correlate them to severity, because everything is based on the physical model. We use the dynamics of the train responses. So this feature actually has a physical meaning. So in summary, we were able to identify the track profile features by separating out the vehicle properties from the train vibration responses using sparse approximation, and reduce the feature dimension significantly for 100,000 times. And using this feature, we were able to detect the changes happening in the track status using the train vibrations. And we achieved 92-93% accuracy with that. And furthermore, can characterize the damage happening on the track. We can localize where the track is happening. We can quantify it using the physical properties of the features. And currently, we've been working on also monitoring the bridge damage state, the railway bridge damage state, using the train vibration responses. Because when the train is traveling across the bridge will vibrate. So the train responds, in addition to the engine noise and the interaction between the track surface and the train, it will also have the bridge vibration added to it. So for that, we just did some experiment on the Panhandle Bridge and the Monongahela River, I think the south and the north side of the river. So to see how much of a bridge information we can extract out of the train responses, we actually went out and instrumented the bridge. So the train runs from 6:30 a.m. to 12:30 a.m. So on one Saturday night at 1 a.m., we went out to the Panhandle Bridge with the Port Authority people, with our PhD student, Ping Xiao, sitting there. And the first picture here shows that we're putting the sensors on the bridge as a reference signal. And then we also put some sensors inside the train. And we made the driver drive back and forth, I think 50 on this bridge, and with different loading conditions. So to change different environmental conditions, we actually loaded the bridge with different number of trains. So we parked one train there and drove across. And then we parked 2 trains there and then drove across. And then we got rid of all the trains and drove across. That was a fun night. I think we were riding like 100 different times. So we're currently analyzing that data so that we're working with traffic training on this project. Okay. So I talked about using vehicles as sensors to understand the surrounding infrastructure state. I think my time's almost up, but I'll briefly introduce another project where we use the vehicle response to monitor human state inside the car. So you know that very stressed driver or very relaxed driver will both increase the risk of accidents driving the car. So one way of understanding the driver's status, like attention level or stress level, is to monitor their heart. And there's something called the RR rate. They see the interval between the peak in the heartbeat. And you can look at the variability of RR rate and also the frequency of it. And when we put the vibration sensors in the car to measure the vehicle responses, it also measures the vibration caused by the driver's heart. It's a very small signal, but it does impact the signal. So here's an example of the signal we collected. The first figure is when the car is idle. Second figure, when the engine is off. Second figure, when the engine is turned on. The third figure is actually driving and the driver is laughing and talking. So a lot of noise. So if you look at it visually, the first figure, you can pick out the signals due to the heartbeat. But the second and the third one is pretty difficult to figure it out unless you know that it's there. So we have to develop a lot of signal processing, similar to how we decompose the signal for the train responses. And combining the physical model with the machine learning, we can actually extract this RR curve rate from the driver's heartbeat. So that's another project we are working on with. So the overall summary, I talked today about using vehicles as sensors to monitor what's going on within, like driver stress level. We can also monitor what's going on about the vehicle itself, like the vehicle performance, and understand what's going on around, like the road, track, and bridge conditions. There are other projects ongoing in my lab where we use the buildings as sensors to understand the occupant status. So occupant walking around causes vibration in the building. By measuring building vibration, we understand occupancy, occupant health status, and some of the cognitive states of the occupants. We also measure the structural damage state and the traffic condition outside the building by measuring building vibration. And finally, we also have human body as sensor project where we measure the vibration happening on the skin surface of the human body and do the muscle activity and fatigue level monitoring. So all these projects are based on the idea that we're trying to indirectly monitor different kinds of information through measuring the physical structural responses. So I'm gonna actually skip this slide and I'll finish by thanking all my collaborators from different departments and also industry and government partners. And last but not least, my PhD students, because all of these things are actually done by our students. So, and also the funders and the deployment partners. So that's it for me today, and I'll welcome any questions.
Yeah, a number of years ago, I don't know if it was in Mississippi or Alabama, but barge hit a bridge on the track. And then a little later, Amtrak train went over into the river. And I think maybe 30 or 40 people were still killed. So these sensors today, could there be a sensor on the bridge and the track and then relay that information to the Amtrak train on the so it could have slowed down? Because even with the bridge, the Panhandle Bridge, something like that possible.
That's possible. Yeah, if you have sensor on the bridge, you can probably detect something hitting into it. If you also have sensor in the train of that crashed train, it will know that something happened to the train. So you send a message, then all the following train will be.
Is there anything about like the view aspect of like the railroads that you can like infer something from that? Like if you have a camera in front of the train and it's like moving,
Uh-huh.
can you pick some information about the rails?
Uh-huh. Yes, with the camera, it's possible. Actually, we did put a GoPro once, like in the train car, and it was pointing down at the tracks to see if you can find anything. And with the vision algorithm, it's possible. The challenge will be like different lighting condition and the weather condition will change the thing, and often the cracks and defects we're looking for can be very minute or it could be hidden underneath. So it may change the structural responses, but it may not be visible on the surface, then it will be the challenge.
And how expensive are the sensors?
So these sensors, it depends. If you buy a sensor for research purposes and you buy one or two, this could cost like $500 or $1,000. We do try with the MEMS sensor that's like a couple bucks, very cheap sensors, and did a comparison experiment. It's not good at picking up the high frequency responses. The lower frequencies are pretty comparable. And I assume if we do a mass production, like make it into a product and order it in mass, then it will become a lot cheaper.
How many sensors do you need per train?
Per train, again, for research purposes, we put a lot of sensors in and see what would be the minimum number of sensors or what would be the good location to put it in there. So currently we have, in one train, we have one triaxial sensors outside the car on the truck, meaning there's no suspension. It's unsprung part. And inside the car, I think we have 3 sensors inside the car. Yeah, so that's the suspension after passing the suspension, sprung part of the train. So we could probably, if you have one sensor in there, I think it's possible because it's collecting the historical data over time.
Thanks for speaking. This is very interesting. To clarify, so what you're trying to do is not necessarily related to track condition. It's related to the infrastructure holding the track, so bridges, etc. So are you looking to your Port Authority partner with you in piloting this out, but it seems like someone like PennDOT would be the one that would be interested in actually collecting
Yeah,
that
definitely
information.
they'll be interested as well. So we do look at the damages happening on the track
Mhm.
as well as the supporting structures, which could be the substructure for the bridges.
Mhm.
So for bridges, I heard PennDOT would have a lot of interest in bridge maintenance parts, so that could be a potential good partner.
Mhm.
Yeah, we're also interested in extending it beyond the rail for the train.
Mhm.
So when we put it in the car, it can be just the regular highway or freeway monitoring with the bridge monitoring, car bridge monitoring. Any other questions?
So you mentioned when it came to user interaction in cars and behaviors, it picks up your heartbeat as well as other vibrations. So where is the sensor placed so that you actually can pick up the heartbeat? And also you mentioned that it's very like difficult because it's weaker compared to other vibrations. How can you actually distinguish the heartbeat from other like vibrations?
So for sensor location, we've been trying on different locations. So I mentioned the sensor outside the car itself next to the wheel like axle. So that's one location. Another one is the sensor inside the car on the floor. Another one is on the car seat. And then we have fourth one on the seat belt. Of course, seat belt will have the best response regarding the heart rate. But then everyone has different height. And then sometimes depending on your body condition, it may not work well. The seat one is also pretty good, unless your body is actually touching the seat. Sometimes some drivers will drive like this, and something in the back matter. So then it works. So as you go to the floor, it works well if the if the engine is off, or even if it's idle. So if you're driving and there's pump outside, it's still a challenge. It's an ongoing project now. For outside, we haven't tried heartbeat with the sensors outside. It seems very difficult. Another thing we tried is if the person is sitting on the table or on the seat, the regular room, and we have sensors on the floor, and it does pick up the heartbeat of the person. We were actually pretty surprised how sensitive these sensors are.
Thank you. Any other questions?
Yeah, like if you ride Amtrak, you kind of overhear the conductors walkie-talkie. It'll say, mile so-and-so, no defects detected. And I'm just wondering how those sensors are different than these sensors.
Do you know what kind of sensors they're using?
No, when I ride the train, I'll hear that.
Uh-huh.
And it seems like they check it every mile or whatever. I can't, it's just
As
periodic.
they're traveling,
As they're
checking
traveling,
it.
right.
They have some like scanner inside. I'm not like very familiar with it. Because usually a lot of inspection is done on a special car. They have a specialized bogey, and you put laser scanner and all the stuff, and it travels very slowly.
Right, but this is just on the train.
Uh-huh.
They'll say that every so often.
Nice. That could be some information needed from the central location who already has the inspection law. Yeah, I'll be interested to find that out as well.
I have a follow-up question. So, have you taken a look at the state of different onboard sensors with different vehicle types that where there could be existing vehicles with onboard sensors that could already sort of transmit the data that you're collecting and sort of be processed in this method?
Some vehicles do have onboard sensors measuring vibration responses and other information about the vehicle. The challenge was we couldn't get access to it because of security and other reasons. That's why we have to bring in our own sensors and get the data from our fleet. It would be nice to compare our sensing data with already existing onboard sensor as well. For regular, like commercial cars that I drive or you guys own, it does have sensors in there as well. I think the sampling frequency is probably lower. We do sample at pretty high frequencies to see what kind of different information is embedded in different bandwidth. So that could be the difference, but in the lower frequency range, the information could be similar. Any other questions? That's it. Thank you.
Did you know?
No, I.
It was so worth it. I like your Snapchat that was like,